Okay, we have a statement here that for any n greater than or equal to 0, 3 to the n is greater than n minus 1 cubed. Now, just to show you a couple ideas what you could do here, you could show that p of 0 is true by plugging 0 in and showing it's true. You could show p of 1 is true, p of 2 is true, and then maybe p of 3 is your base case, and you do um, and you do induction then from there on. Or you could have P of 2 as your base case and then have everything from then on out. So you don't necessarily have to have 0 as your base case here. However, if the same logic applies for 0 as it does for 1, as 2, 3, so on, it's usually easiest to take the lowest integer that you're being asked to prove it for and use that as your base case. So let's do this proof by induction on n. Um, so P of 0 is true because um, three to the 0 is greater than um, so what I did here, I could have written just this first, which would be plugging in 0 for n here. And then I said 3 to the 0 is 1. This one here is negative 1 to the third power, which is negative 1. Because I kind of saw what was happening here, I went ahead and just put, okay, 1 equals this, which is greater than this, which equals negative 1. And this is a true statement because 1 is greater than negative 1. So we know that this statement is true. Again, you didn't have to do it this way. If you wanted to, you could have just plugged in the 0 on each side and then rewritten that inequality to show that 1 is greater than negative 1. In any case, the statement is true for p of 0. So now we assume pk true for some k greater than or equal to 0. So 3 to the k is greater than k minus 1 cubed. Now, again, it may feel like cheating. You may be like, well, how can you just say that? You could just put any statement in here and then your p of k would be true. Well, we're assuming that p of k is true, but if it would end up that p of k plus 1 is not true, then we'd kind of have a um, proof by contradiction. In other words, the p of k would no longer stand as being true. So remember, we're not trying to prove that p of k is true. We're just taking that as our assumption to get this induction machine working. And if this really does turn out to be that p of k plus 1 is true also, and we had our base case true, then we can kind of attach that machine to the base case and let it ripple out throughout the positive integers. So what are we trying to show? What's our finish line? We want to show that, so again, we're just doing the same as the p of n. This is our p of n statement right here. And I could have written that out just for clarity, but this is our p of n statement. So we want to show that 3 to the k plus 1 is greater than k plus 1 minus 1 cubed. In other words, what I'm doing here is I'm coming in from the finish line and I'm bringing it closer to the starting line. I'm rewriting this statement so that if I get there, I know that I'm done with the proof. In other words, we want to show that 3 to the k plus 1 is greater than, since it's plus 1 minus 1, what we really need to do is show that 3 to the k plus 1 is greater than k cubed. So how are we going to do that? Well, remember, we have this as a starting line. We know that this is true. So multiplying, since this is true, we could multiply both sides of this by 3. Multiplying both sides of our induction hypothesis by 3, we have, and why am I doing that? Because I know that this is true, or I'm assuming this is true, and I'm trying to show this is true. So I want them to look like each other. So right now the left side is 3 times 3 times 3 times 3. It's k of those 3's, and this is k plus 1. So I think, well, if I multiply both sides by 3, at least the left side will look very similar to what I have, even if the right side doesn't quite yet. So we would have 3k plus 1 is greater than 3 times k minus 1 cubed. Okay, well, this is progress. Somehow we now have to show that this is greater than or equal to the k cubed. How can we do that? Let's go ahead and expand this out. So this would be the same as 3 times. Now I'm just going to expand this k cubed minus 3k squared minus 3k plus 1, or sorry, minus 1. And how am I getting that? Well, if you don't know that expansion, you can always do it off to the side here. So k minus 1 squared would be that. And then we'd have k minus 1 times k squared minus 2k plus 1. So we'd have k cubed, then we'd have minus k squared and minus 2k squared. That would give us minus 3k squared. I'm just using distributive property here. We'd have minus 2k squared, or sorry, I already did this one. So we had our k cubed, and then we had minus 2k squared and minus 1k squared. And then we have our positive k plus 2k. And then we have minus 1 at the end. So it's good I multiplied that out. Found a little algebra mistake there myself. So that's a plus because we have minus 1 times minus 2k, so that's plus 2k. And then we had this k times the positive 1, so that's how we get that. Okay, so now we can distribute the 3 to get 3k cubed minus 9k squared plus 9k minus 3. So how do we know that this is greater than or equal to k cubed? I mean, it could be that this is a pretty powerful term here, right? So here's where I think we can, let's do a little side work. So we want to show this is what we want to show, that this is greater than or equal to k cubed. Well, we could subtract a k cubed from both sides, so essentially we're trying to show that this is true. All I'm doing here is subtracting k cubed from the right side and subtracting one of them from the left side. And you can add or subtract anything without changing the greater than or equal to sign. You can also multiply and divide, but there, if you're multiplying or dividing by a negative, you do have to change the direction of the sign. So why do we know that this is true? Good question, Daniel. Good question. Well, there's a couple ways we could reason it. One, we could put it into Desmos and see what the graph of this does. Let's do this. Let's divide by k cubed. So because we're dividing by k cubed, this has to assume that k is greater than 0. So this is not going to work if k equals 0. Okay, so I'm realizing that this is not true for k equals 0. If we plug in 0 for k here, we basically get -3 greater than or equal to 0, which is not true. So what I'm realizing is back when I made that first statement, it looks like I probably should show p of 0 separately, then have p of 1 be my base case, and do that. So what we're going to do is, what we're going to say is for k greater than or equal to 1, we can divide by k cubed. We couldn't do that for k equals 0 because you can't divide by 0, but as long as k is a positive number, we can divide by k cubed, and we'll get 2 minus 9 over k plus 9 over k squared minus 3 over k cubed. Now here, as long as k is a positive number, what's going to happen to these? Well, this has to be okay, and I'm running into problems here too, because what I want to happen is I want this to be less than or equal to 1. So in order for that to happen, I'm going to have for k greater than or equal to 9. Now, if k is greater than or equal to 9, then we have this equaling 2. We have this as less than or equal to 1. And this one right here is also less than or equal to 1. So the two things that are getting subtracted from my 2 are both less than or equal to 1. And then I'm adding a little bit on. So no matter what, in this case, I'm greater than or equal to 0. I have 2. I'm getting up to 1 subtracted, and up to 1 subtracted here. So the most possible I could get subtracted is 2, and even that's not really obtainable. But the point is I can't get more than 2 subtracted. So here I'm staying at least at 0, plus I have a little bit added on. So at this case, no matter what, I'm greater than or equal to 0. So I can say that this is greater than k cubed, and I've completed my proof if my base case is 9. So I'm going to have to do this for a base case. So remember when I said I was going to have to potentially do some base cases before I let the induction machine take off? Well, the way that I did this proof, I've shown that it's true for p of 9 on up through infinity, but now I have to show it's true for, well, I've shown it for 0. I need to show p of 1, p of 2, all the way through p of 8 are true. And I can do that just by checking them. I mean, 3 to the first is greater than -1 cubed. 3 squared is greater than, whoops, sorry, 0 cubed. Then this would be 2, 1 cubed. And I go down here to 3 to the 8th is greater than 7 cubed. So I showed these base cases separately, and then my induction proof takes off from p of 9.